So this will be the 18.5, how we can predict spontaneity. We will look at the Gibbs free energy, standard free energy changes, and using the Gibbs free energy and the standard Gibbs free energy, we will solve problems. So one of the important formulas for us to remember is that let's go to this one. So this is the one important formula for us to remember, but the Gibbs free energy is connected to the delta H, the enthalpy change of the system, and the delta S, the entropy change for the system. And we have a temperature component here in Kelvin. So delta G, the free energy, Gibbs free energy, the formula is delta H of the system minus T delta S of this system as well. So for the reaction to be spontaneous or happen by itself without any outside intervention, the sign of delta G has to be negative. So if the delta G has a negative sign, that means the reaction will happen spontaneously. If delta G is positive, then the forward reaction is not spontaneous, but the reverse reaction is. So, and that's what we have here. Delta G less than 0, reaction is spontaneous in the forward direction and non-spontaneous in the reverse direction. When delta G is positive, the reaction in the forward direction is non-spontaneous, but is spontaneous in the reverse direction. But when delta G is 0, the reaction does not really proceed in any direction. It's just at equilibrium. It's just at equilibrium. In this table, you will not be able to memorize this table, of course, but it just tells you when delta H is negative and delta H has a different sign and delta S is different sign. Will delta G be ever negative? Will that be ever negative? Because for the reaction to be spontaneous, we want a delta G to be negative. So look at the first one. Delta H is negative. That means the reaction is exothermic. As a rule, the exothermic reaction, most of the exothermic reaction, they are spontaneous. And when delta S is positive, it's also reaction should be spontaneous. So when we have those two components, negative and positive, then the sign of delta G will always be negative. And that means this process always will be spontaneous. If you look at the example, hydrogen peroxide, they always will be decomposing into H2O and oxygen, regardless of the temperature. So if I will go back over here, so if this H is minus and delta S is plus, so minus and minus will make delta G always negative. I mean, it's not negative, it's just I have a sign of minus, meaning energy is released, and take that energy and do something with that, useful with that. So when we have the reaction is endothermic, delta H is positive, and delta S is also is negative, delta G always will be positive. And that reaction will never be spontaneous, never. Take a look at this one. Oxygen gas does not spontaneously change into the ozone, but what is spontaneous is the ozone can change into oxygen. So let's go back over here. So if this is a positive and delta S is negative, negative and negative makes this part positive, and delta H positive, the positive and positive, they will never make delta G negative. So that reaction, when it's endothermic process, delta H is positive and delta S is negative, that reaction will never be spontaneous in the forward direction. So that's the case here. So now let's take when the delta H is negative, it's an exothermic reaction, but in this case, delta S is negative as well. So will that delta G ever be negative? Yes, delta G can be negative only when that T delta S, when T delta S is less than delta H. So let's go back over here. So take a look at this one. When this is negative, we already have this part negative. So delta S is negative, right? So the negative and negative makes this positive. So this is a negative, but the second part becomes positive. So yes, delta G can be negative because I have a delta H negative, but it only can be negative if T temperature is low. Then the absolute value of delta H will be greater than the absolute value of T delta S, and the delta G will be negative. So it has a possibility to be spontaneous only when the temperature is low. So at the low temperature. So, and that's an example. Can H2O liquid freeze and become solid? Yes, it can only if the temperature is low. It cannot happen if it's a high temperature. And then we have a delta H positive and delta S positive. Can delta G ever be negative? Yes, it can be negative, but the temperature has to be high. So this is a positive. This is a positive, but delta S is negative. This is minus and minus. Makes this one I'm sorry, this is a positive, right? Minus and plus will make this part negative, although delta H is negative. So we need this one, T delta S, to be higher in the absolute value than delta H, but it only can happen if the temperature is high temperature. So that process can be spontaneous at the high temperature. And take a look at this example. It's a mercury oxide. Can we decompose it into mercury and oxygen? Yes, it can happen spontaneously only when the temperature is high. So it's good to understand this equation. You need to get the negative delta G. So look at the possibilities of delta H to be plus and minus, delta S to be plus and minus, and when and if delta G can ever be negative. And this is they're giving you an example. Um, and they're giving you an example. A reaction will be spontaneous according to that table if at high temperature, if both delta H and delta S are positive. So yes, so delta H is a positive, delta S is also is a positive, and now we need to determine the temperature above which the reaction is spontaneous. So delta S, you have to know, a lot of times it's just in the joules, and delta H is a kilojoules. We have to bring them to the same unit. So we take 476, we convert it to kilojoules by dividing by 1,000 joules. And then we can find the temperature, delta H over delta S, at which higher than that temperature will make the process spontaneous. So we're just converting it to Celsius in this case. So now this is, again, predicting spontaneity. We will talk about the standard free energy change. We did talk about the standard condition when we talk about the standard enthalpy change. Standard enthalpy, it's in semester one. We talked about the standard enthalpies and how we define standard enthalpies. It's a chapter 5 of this textbook. So the standard free energy, this subscript here means it's a standard. It's when the reaction occurs on the standard state condition. First of all, when reactants in their standard state are converted to products that are also in their standard state. So once again, what is a standard state? If you have gases, the pressure of the gases has to be 1 atm. If you have a liquid, it has to be pure liquid, solid, pure solid. Elements, the elements has to be in their most stable allotropic form at 1 atm and 25 degrees Celsius. Let's say if you have, let's say, oxygen, it has to be O2. Or if you have a carbon, it has to be carbon graphite, not carbon diamond. And if you have a solution, the concentration has to be 1 molar. If we have those conditions, then we have a standard state conditions. So, and this is just the equation, just the regular equation, A plus B makes C and D. You probably saw and remember a similar equation for the standard free enthalpy change. It's the sum of the standard free energy formation of the products. Of course, we have to use their coefficients here because the standard free energy of formation is for only 1 mole. But if you have a coefficient other than 1, you have to multiply it by that. So the sum of the standard enthalpy of formation of products minus sum of the standard enthalpy of formation of reactant, that's what you have. So delta G standard formation, it's a standard free energy of formation. It's a free energy change that occurs when 1 mole of the compound is synthesized from its elements, and those elements are in their standard state. So that's the formula. Similar to that formula, we have a formula for the enthalpy, and the similar we have for the entropy. So again, take a look at this equation. Carbon, the stable allotrope of carbon is graphite plus oxygen gas. It makes CO2 gas. How can we find the standard free energy of formation of this reaction? We will take standard free energy of formation of product minus sum of the standard free energy of formation of the reactants. So since this is an element, carbon and graphite, they're in their elemental state, their standard free energy of formations are 0. And for this reason, the reaction, standard free energy of reaction is just equal to the standard free energy of formation of CO2. So you can look at the similar sample problems. You have it in your textbook and Alex with the explanation. It's good to look at the explanation and to understand them. So now let's take a look at this reaction, and we can use delta H, standard enthalpy of reaction, and the standard entropy for this reaction, and find the delta G. So in order for you to find for this reaction standard enthalpy, we need to know their standard enthalpy of formation of all of those substances. And as I said, there is a similar formula to the standard enthalpy of formation. So this is the standard enthalpy for the whole reaction. This is a standard entropy for this reaction, but we need to know entropies of all of those component substances here. So we find them, and then we will be using this formula, delta G equals delta H minus T, delta S. So delta G equals delta H, we found the delta H. Let's say temperature is 25 degrees Celsius, we convert to Kelvin to 98 K. Delta S we just calculated. So we're getting that delta G equals a positive 130. So because delta G is a large positive number, the reaction will not proceed spontaneously in a forward direction. It will not favor product formation at that temperature, 25 degrees Celsius. We can find the temperature. We can find the temperature when delta G will become negative. We'll say, let's say that delta G, it's equilibrium, and let's find out temperature where we have the reaction at equilibrium. So when delta, it's equilibrium, delta G is 0, then we can find the T from here, and we'll find that the T for the equilibrium is 1108 Kelvin. But when the temperature is greater than that temperature, then delta G will become negative, and we will say that the reaction will proceed forward, and it will favor formation of the products. Okay. Yeah, it's that's what it says here. As the temperature at which the phase change occur, the system is at equilibrium, and then delta G is 0. So you can always find the temperature for the equilibrium, or you can find the delta S. So at 0 to 73 K, 0 degrees Celsius, delta S of ice to water is 22 joule K per mole. And for the reverse process, of course, it's a minus. So at 0 degrees Celsius, ice will turn into the liquid water. And at that temperature, the delta S is equal actually negative 22. So once again, you can look at the sample examples. You can follow them on Alex with the explanation.